Good day, everybody. So let's take a look at certain topics from our organic chemistry efforts. And we're going to cover the topics from the skeleton formulas up until very basic reactions of alkanes. So yeah, to begin with, so I'm going to look at some problems here. Let's take a look at the connection between the skeleton formulas, expanded and condensed writings of alkane structures here, right? So yeah, as an example, so let's say we have like problem one, item one, whatever it's going to be, right? So let's take a look at the condensed formula of the following compound, right? So maybe we'll call it A, right? So here we have it, right? So we'll have our good old alkane chain that will look like this. And then all of a sudden we are going to add the functional group, right? So if you look at this functional group, so here it is NH2. You should be able to recognize it as the amina group or amine, right? And here we have it, right? That is one of the possible structures that contains three carbons in the alkyl chain or part of this whole compound, and also has the amina group, right? So what can we do with that? So if we think about it, so some things can be potentially asked, right? Or you can just use that thinking framework and just play around with various other structures that you can randomly write, right? So yourself, but of course they should make sense, right, in terms of valences of the carbon, for instance, as well as other atoms, right? So there are some general rules to follow, but also there is latitude that you can exercise. So what is this latitude about? So first of all, we can, for example, show the expanded formula for this compound. Let's go ahead and do that. Right, we'll convert our condensed structure into the expanded one. So the expanded structure will just basically show all the possible bonds between the or amongst the atoms, right, that you can see in this molecule, right? So we'll have our NH2 group expanded. So we can also show the lone pairs, right? It's always a good idea to show the lone pairs as necessary, right? So especially if it's asked in questions, right? Sometimes it can be a little bit fuzzy. So, but just look at the questions. If it comes to the exams, in our case, I'll try to be kind of as specific as possible in the questions, right? And then say, okay, well, show the lone pairs as necessary. So, for example, there are no lone pairs on the carbons in these cases, right? So, but there are lone pairs on nitrogen atoms, for example, in amino groups. So show them. And then if anything, it's similar to NH3, if you think about it. So because it's this compound is nothing more than a derivative of NH3 in a sense, right? So now we're going to beef up the carbon with the hydrogens, right? So that we can see in the condensed structure, and we're going to form the expanded structure like that. So pay attention to the fact that the carbon here has 4 valences, right? So that's kind of the general theme about all the carbons in organic compounds. So of course, we can have various combinations between carbon and then other atoms. So maybe we'll have CH3, right, connected to like other carbon. Maybe we'll have CH2, right, connected to other carbon. And then also it's going to be a good idea to like know what those groups are called, right? If you have CH3, CH2, and CH, for example. Again, so like what you can think about, okay, well, you see some things, right? So, but oftentimes they are called, yes, of course, we can read them as like CH3, CH2, but also we can read them in a more like rapid fashion as methyl, methylene, methylene, amine group, right? Or amino group. So they can be used kind of interchangeably at this point, right? So 4 valences on the carbon, 1 valence on hydrogen, 3 valences on the nitrogen, right? So just like NH3 is trivalent. So same thing here, you have 1, 1, 3, right? So 1, 2, 3, 3 valences total. And then the nitrogen is connected to like 1H, and 1 carbon here. So yeah, this is our condensed, expanded. So now we can go to the skeleton structure, right? So this is just about drawing lines, essentially, line angle structure. So the lines and angles, as the name implies. So let's do that. So we'll start with the dot, right? And then we'll be drawing the bonds. So we need to have 3 carbons total, right? So we have 1, 2 carbon, and that's our 3rd carbon right here, right? So 3 carbons are accounted for. So then we'll see the bonds between the carbons here, right? So the carbons and hydrogens are not shown in this case, but if you have the functional group, you will need to like show the atoms, the header atoms in that functional group. So in this case, we'll have the NH2. So we'll connect it to this carbon right here. So, and then we can show it as a NH2 like so. So yeah, this is our condensed, not condensed, but skeleton writing of this particular functionalized carbo, or not alkane, let's put it that way, functionalized alkane, right? So we have CH3, CH2, CH2 again, and NH2. Okay, so now let's take a look at something kind of like more long, so to say, right? So in this situation, we can switch gears to maybe just a longer chain alkane, right? So let's just remove the functional group and then see what we can do, right? So we are going to start with a condensed structure. So that will look like this. So maybe we'll have something like CH3, CH2, CH2 again, CH2. So it's going to be a bunch of methylenes. So we'll have already 4, let's say 5 carbons in a row, right? And then let's add one more, right? So here we go. So we have 1, 2, 3, 4, 5, 6, 6 carbons, right? So again, start with the dot, okay? So then this will give you kind of like the basis to draw, right? So we'll be drawing more lines like so, and then we'll be counting carbons. So each terminus and the angle, right? So will be counted as a carbon. So there's a carbon here, another carbon. So we have 2 carbons, 3 and 4 carbons already. So then we need to have 2 more, I think, right? So to make it 6. So that's 5 and 6. So these are our 6 carbons right there. So, and then that's enough to show this alkane with the 6 carbons in the chain, right? So then everything else is implied by convention, basically. So here is going to be your CH3, then CH2, 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 CH2. So you have total of 4 CH2s. 1, 2, 3, 4. 4 of them, right? You have 2 methyls, which are terminal. Methyl and methyl. So yeah, that's okay. Everything is accounted for, right? So yeah, basically, if you think about that, so this is nothing more than just growing from the ethane, right? So ethane will be kind of like the simplest representation, I think, which is different from just a dot, right? That would be like methane, but it's very rare to show that just the dot, right? So methane is just shown as CH4 or carbon with 4 hydrogens on it, right? But ethane, you can show it like that, right? So then if you want to do like that's going to be your CH3, CH3 here, right? If you want to do propane, then propane will look like this, right? So you'll just continue drawing from ethane. So you will add one more line here, right? So this will mean that you have propane, CH3, CH2, CH3 or methyl, methylene, methyl. So this will be nothing more than CH3, CH2, and CH3 again. So these are our kind of like conversions from the condensed structure to the skeleton or like line angle structures, right? So then let's now try to finally make a branch of some sort, right? So what we're going to do is that we'll keep this 6 carbon chain, right? And maybe let's make it 7, right? So because why not? So we have it all here. So let's switch back to the pen, CH2, CH3 again. So I'm gonna do a little bit of the erasing here just to kind of draw everything anew for the practice purposes, and that's okay. So yeah, again, so just a reminder, You can like watch that forever, right? So, but it's always a good idea to write it yourself on a piece of paper, a whiteboard, maybe a white like piece of paper would be ideal. So because our exams or many other exams are on the piece of paper, and you will be required to draw something, right? Maybe it's going to be your lab notebook of some sort at work, whatever it could be, medical practice, and so on. And then you'll be required to draw some structures in there, right? So by hand, using ink and paper. So just get used to that situation. So anyway, now we're going to get used to the branched chains. So we're going to do a little bit of erasing here. Let's maybe add some substituents, right? So here, like for example, so we'll have a couple of substituents. So maybe they will look like that. So let's do something random, such as here we're going to introduce CH2 and CH3, right? And then here we'll have a methyl group, for instance, and then maybe on the fourth carbon, we'll have something else, right? So these are the bonds here, and let's add something else to the third carbon, for example. So we're going to do a little bit of the erasing again. So maybe here we'll have, I don't know, like what you're going to have here, maybe CH2, CH2, and CH3. Okay, so let's make it like very branched, right? So with a variety of substituents. So anyway, so what we're going to do is start with the main chain, for example. We have 3, 4, 5, 6, 7 carbons, right? So start with a dot right here. No, that's not what I wanted. And then we'll continue with the lines, right? So then they go ahead and then they kind of are connected. So you have this like 120 degrees angle, and you just keep drawing, right, until you run out of the carbons in your main chain. So we'll have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, right? You can show the termini and the angles with dots, right? Just to kind of emphasize that new writing pattern for yourself. Then if we start counting from, let's say here, for example, right, that's okay. So let's say on this like second carbon here, so that's our second carbon, we'll have the ethyl group, right? So let's show it. So we'll show the connection. It's going to be carbon-carbon bond here. CH2, CH3, done. CH2, CH3, right? So, and then you can see the pattern, right? So yeah, for example, if you see this kind of like vertex, right, that is just comprised of two lines at 120 degrees angle, so that in this vertex, you will have CH2 group, right? So, and then, yeah, you can also convert just for yourself this line angle or skeleton structure into the full structure, right? So the expanded one, in which you show carbons and hydrogens, but just do it yourself, right? Just in the interest of time. Okay, so we have our CH2, CH3, that's ethyl here. So then let's imagine that's going to be our third carbon that features the propyl group, right? So 1, 2, 3. Carbon 3 is here, right? Well, let's show the propyl, right? So we're going to keep those 120 degrees angle, 120, 120, 120 again. So, and we are going to show it like that. So that's going to be so that's probably too much. CH2, CH2, CH3. Oh, no, that's enough, right? So we have methylene, methylene, and methyl again. So you see, it's easy to use the terms, right? So we have vertex, vertex, terminus. It's carbon, carbon, carbon. And then we just need to kind of like assume that, okay, well, these are two carbon-carbon bonds, and then the leftover things will be two H's, right? So the H's, hydrogens are not explicitly shown, but if you had, for example, on this CH2, instead of CH2, you have two fluorines, for example, F and F, right? So then you'll have to show them explicitly. So because it is a heteroatom, hetero means different from what? Carbons or hydrogens. So then, moving on, there is nothing on the fourth, nothing on the fourth. So fifth carbon has something. So, and then this something is CH3. So let's just show the bond, right? And terminus. So terminus here will stand for the carbon. So here we have explicitly one bond to the carbon, nothing else is shown. Then carbon, we also know that it has to use 4 valences, right? So consequently, 3 more valences are available. Available for what? If nothing is shown, then it has to be hydrogens, right? So then you see it kind of becomes repetitive. You see those patterns again and again. So, and again, just for your own practice, you can just imagine some structures and draw them. So then we have the 5th carbon with the CH3 on it. Then we have CH2 and CH3 left over. So that's going to be 6, 7, let's imagine, right? 6 and 7, there is nothing on them. So that's your like branched alkane right there. So it's still alkane, only carbons and hydrogens are engaged into that structure. So perhaps it was our structure B. So yeah, that's kind of as far as these topics are covered. So here you can think about what happened, right? So it was expanded structures, condensed structures, and skeleton structures. So that's what you kind of easily can draw on paper, right? So, and then, yeah, it's always a good idea to practice it yourself, right? So you don't have to necessarily wait for some sort of like practice sheets. They will show up eventually, right, in one form or another. So, but for now, just kind of like draw some sort of like very long chain alkane, attach some substituents. You can use some header atoms as well. You're welcome to do that, right? And then draw that in 3 ways, right? Such as is going to be, for example, expanded structure, condensed structure, and the line angle or skeleton structure. So that's all good. So now let's take a look at the further topics. What else do we have here? So the next one will be the substituent information. So yeah, we'll just build up on the structures right in, and then we're going to modify those structures in a particular way. So let's say we are going to erase these parts here and see what we can do, right? So let's start with, let's say, the propane, right? For example, just to have something more basic than just ethane, right? So here we have something with more carbons. So that's your propane, CH3, CH2, CH3 again. So what happens? So what could happen is the removal, right, or the separation, as somebody once said, of the hydrogens and the departure of said hydrogens. Okay, so where is the what do I want? I want to erase. Okay, so here we go. We'll have CH2 and CH3. All right, so now and that was not quite necessary. So we're going to show just the expanded structures at this point. So originally we had hydrogens everywhere. But then what happens is that one of the hydrogens can be removed, right? So let's say we're going to remove the hydrogen from here, from the terminal carbon, right? So we're going to look at the bond, right? So that's comprised of 2 electrons, and we're going to break this bond. So now we're going to make a new structure, which is going to be looking like as CH3, CH2, those parts remain intact. And finally, we have CH2, and then we'll have the dot on the carbon, right? Sometimes it's good to it's okay to show the dot here next to hydrogen. It will be implied that this electron still is present on the carbon because everybody agreed that hydrogen can only make 1 bond, right? So yeah, if the hydrogen is broken off, then that's it. So, and then, yeah, there could not be any free electron on the hydrogen because those 2 H's are bound to carbon, right? So if you see the electron or the dot, let's say here, for example, right, and then not on the carbon, then it's okay. So it's implied that this electron belongs to the carbon, right? So, and then here you have the propyl group, right? So the hydrogen departed, you have the propyl group. So now we can have something different, right? So which is going to be a different functional, not different, but a different alkyl group, right? Alkyl substituent, as we can call it. So let's try to break another bond. We're going to break this bond now. So at the carbon or the methylene in our propane, right? So what's going to happen is that we're going to now have a slightly different structure, right? As we break this bond here on the second carbon between carbon and hydrogen, what do we get? So CH3, CH, and CH3, right? And you will have the free electron on the carbon in the middle. So this entire thing, so we have the eraser here, very convenient. So let's just erase it. So, and then that's what we got, right? Basically. So now you don't have this hydrogen with the dot anymore with its electron. It departed, right? So it's somewhere else. So let's just imagine that it's kind of like somewhere like outside, but of course some kind of chemical reaction took place and then everything is balanced. So, but for now we formed the isopropyl, right? So if you think about it, so it's a different structure already. Why is it different? So because of the placement of that like free electron, right? So here, those things are isomers, right? If you think about it, right? So they have exactly the same sort of like material composition, right? So 3 carbons, then they all have like whatever it is, 7 H's, right? And they have this free electron on the carbon. But in this structure on the top, right? So we have the free electron on the terminal carbon, right? So in this case, we have the structure, the free electron on the carbon in the middle, right? So then if you think about like the placement, right, of the building blocks, then the placement is different, right? So it is as if you think about maybe, let's say, you have, let's say, like yourself and some sort of frisbee, for example, right? So then you can have a frisbee in your right hand, right? So that's going to be like one situation. But you can also have a frisbee in like the same you, right? But you will have a frisbee in your left hand. Then it's going to be already a different composition, right, of you and a frisbee. Or maybe you can have yourself and somehow you hold a frisbee with your right foot, for example. It's the same composition as you and frisbee, but the placement of the building blocks, which is going to be like you and frisbee, is different, right, from one variant to another. Same here. So just think about those like analogies. So those structures are not identical, right? They're isomeric. They're isomers to one another, but they're not identical due to the placement of the building blocks. And you can make up more examples from like real life situations yourself. Okay, so now let's see what's next. So this is the formation of the functional or like alkyl substituents. So that is going to be like true about some like other substituents that you can form, such as butyl, for example. Look at that. So there are many options, right, to kind of like review yourself in addition to that. So this is supposed to be kind of only the springboard for your like future thinking. So because it's something that you need to do like on your own too. So next one, let's take a look at the, I would say, a little bit of slow down here. Sorry for the hold up. So what are we going to do? So we're going to now take a look at the names, right? So naming exercises. So and then it's going to be about IUPAC rules, right? So I'm not going to like list the rules again. So you have them like on the like slides, right, in the textbook and so on. So you can look at those resources. So it's pretty nice. And here we're just trying to go through some examples, right? So again, they will serve as a springboard. We potentially cannot like solve like 1,000 examples here. So that's going to be something like that will be included into the practice sheets, practice exercises that will come out sometime soon, maybe today, so maybe on Sunday or Monday. So, but you will have enough like time to look at that in addition to the exam review. So study guide will be coming out today, by the way. So for those who know what the study guide is about, so that's for you. So if you just randomly watch this video, then don't worry about the study guide. All right. So anyway, so we move to like problem, whatever, it's 3, I would say, right? So then here we're going to take a look at the names. So yeah, let's take a look at some structures, right? So, and then the first structure that we're going to do, we're going to like name it. So let's say structure A, it will be looking like that. So here is going to be a little bit of the trick going on, right? And then this is going to be mostly about you counting the carbons and then identifying the longest chain in this particular compound. CH3 here and CH. All right, so let's take a look, right? So sometimes it's tempting to just look at the like longest like straight chain and say, well, that's the longest one, right? 4 carbons, okay, we are going to move on, right? So, but it's not always the case. So the structures can be like written in a deceptive fashion. The study guide will come out today by the end of the day. So by 5 p.m. you will have it. So for the study guide people. So, but here, yeah, we have it. Okay, yeah, you're welcome. So we have the structure, the long chain that is here straightly written. So looks like it's just 4 of them, 4 carbons in the longest chain, but it's not the case, right? So sometimes the chains can be like angled, right? So which is what we show in this particular example. So in fact, the chain is kind of hidden, right? Because if you count the carbons here, you will have the continuous chain, which is looking like this, right? So that's going to be the way for this longest chain. So you have 1, 2, 3, 4, 5. 5 carbons, in fact, are contained in the longest chain in this situation, right? So then if we have the 5 carbons in the longest chain, the name will bear the part which is going to sound like pentane, right? So 5 carbons in the chain will signify the pentane from the alkane family. So then what else do we have here? So next we'll have the substituent, right? So we need to count the carbons and then we need to count them, start the count from the terminus that is closest to the branching, right? So if you look at this situation, doesn't really matter if you start from the left-ish to the right side or from the right to left, because this substituent here, so that's CH3 group, which is not part of the longest chain, right? That will be substituent consequently, will be on the 3rd carbon no matter what. 1, 2, 3. 1, 2, 3. So it's on the 3rd carbon. So it doesn't matter how we start the count, anything will go, right? So that's 5 carbons. So we'll have the pentane as part of the name. So now we have the substituent here in the circle. What's that? That's going to be a methyl here, right? So, and then, yeah, so let's just write the names. So the methyl is located on carbon 3, right? So another analogy I heard yesterday, so is just to think about that as street addresses, right? So maybe it's going to be 140 Flag Road, right? So same here, 3-methyl, right? So 3-methyl. So the carbon at which the methyl is located, the carbon number will come first before that said methyl, right? It's not going to be like methyl 3, right? So that's not how the convention is set up. So even even though for some of you it might be more convenient, but it's not the case, right? So carbon number 3 contains the methyl. So 3rd carbon contains the methyl. So it's going to be kind of like the placement of the methyl on the carbon chain, right? So on the 3rd carbon, we have the methyl. So, and then we have that like carbon number 3 containing methyl in what? So in the main chain, which will be pentane, right? Pentane. 3-methylpentane. So that's it, done, right? So don't call it methyl 3 pentane. That's not quite what we're looking for. So first the placement, first comes the position of the carbon, then the name of the substituent on that very carbon, and then we'll have the name of the main chain according to the number of carbons that we have in it, 3-methylpentane. All right, so now another example. So that will be like a little bit more evolved. Let's take a look at this guy. So we have here the structure, which looks like this. So by the way, we're going to use here the condensed formula, right? So CH3, CH, So a little bit more carbons in this case. But let's be careful. All right, so ethyl, then we'll have the methyl right here. Then we'll have another methyl right here. Okay, so what's happening in this situation, right? So let's take a look at the longest chain. So if we go down this way, so we'll have 4 carbons, not the longest, right? So then we're going to have maybe like 5 carbons here. So it doesn't seem to be the longest chain either. So now, what else do we have here? So we have 3, 6, right? So then we have 1, 2, 3, 4, 5, 6, 7. Okay, well, looks like we identified the longest chain, 7. So if we go this way, we'll have only 5. So if we go this way, we're going to have 1, 2, 3, 4, 5, 6, 7, right? So 1, 2, 3, 4, 5, 6, 7, or 1, 2, 3, 4, 5, 6, 7. So like either way, so that is going to be the longest chain right here. So then we're going to number the carbons, right? So 7 carbons. If you go this way, like from the bottom, right, up until here, and end up being here, you like end up with a methyl, right? So, and this other methyl will be like hanging out. So if you go this way, that way, here, so same thing, right? It's going to be the identical like chain anyway. So if you think about it, so both of those groups are methyls, so they are identical to one another. So if you count this way, you'll have 7 carbons. If you count this way, you will have 7 carbons, right? You'll have the same kind of like main chain. So 7 carbons. Okay, so it looks like that's going to be our longest chain in this case. So now we're going to like think about how to number this chain, right? So if you start from here, right, from the left side and then towards the right, so we're going to have the branching on the 3rd carbon, right? So if we start from here, right, so we're going to have the branching on the 2nd carbon, right? So if that's our 1st carbon, we'll have still the branching on the 2nd carbon, right? So anyway, so let's start from the right and then we'll go to the left. Okay, very good. So like 1, 2, 3, 4, 5, 6, and 7. Okay, so then the branching starts on carbon number 2 as opposed on carbon number 3. So we'll minimize our numbers, right? So which will signify the carbons to which substituents are attached. So now let's circle the substituents perhaps, right? So here we have the methyl group on the 2nd carbon. So we'll have another methyl group on the 4th carbon. And finally, we'll have another methyl group on the carbon number 5. So there was a question here somewhere. Let me see what is happening. Okay, so can you... So from the right to left to count the carbons. Okay, yeah, once again, so if I go from right, okay, so let's just imagine I'm going to go from the right. So, and then what happens is that, let's say this is going to be carbon number 1 in the main chain, right? There was a question in the chat. So then what's going to happen is that the branching will have higher numbers, right? So let's imagine this is carbon number 1. 1, 2, 3. You start the branching on carbon number 3, right? So then you have, so maybe let's make the alternative numbering, right? So with the red colors, right? So let's say 1, 2, 3, 4, 5, 6, right? And 7. So in that case, yeah, so the branching starts much later. It will not start on carbon number 2, which is here in the black font, right? But it will start on carbon number 3. All the substituents will have higher numbers signifying the carbons to which they are attached, right? So if you look at our kind of like chain marked with the black ink, right, we'll have the substituents counted as 2, 4, 5, right? Remember those numbers, 2, 4, 5. So now if we look at the red numbered chain, let's see what the numbers are like for the substituents. 3, 4, 6. Overall, those are higher numbers than what we have just seen, right? We are trying to make those numbers minimal. So the numbering, if we start numbering from the left side, will not help, right? So it will just increase the numbers of the substituents. Just let's take a look at the black ones, right? So black numbers. So 2, 4, and 5. So 2, sorry, that needs to be the other ink. Where is this? Cancel, cancel, cancel. Okay, finally. So black ink numbers which are supposed to be minimal, right? So 2, 4, 5. Then let's take a look at the red numbers. 1, 2, okay, 3, 4, and 6. So here we have higher numbers overall. So 3 is larger than 2, 4 are equal, 6 is larger than 5, right? So anyway, in terms of the minimization of the numbers, so this first series beats the red series, right? So 2 is smaller than 3, 4 is equal, okay, so no real difference, but 5 is less than 6, right? So we're trying to minimize the numbers which we are going to use which we will end up using in the name of the compound. So that's all it is about, right? So, okay, yeah, great. Yeah, good questions. So glad it makes sense. So yeah, but yeah, that's what we need to do, right? So we need to minimize those numbers. But again, it's just one example. I'm trying to make like a huge one here, so it entails a lot. But again, so you need to kind of like look at this yourself and kind of like write it like on your own as well, right? Just to help with the internalization. All right. So anyway, so now it's a good segue here. Thank you for that. But now we're going to erase the incorrect ones so that they don't provide any confusion. Okay, so that's like this series wins. This one loses. All right, so now let's go with the substituents, right? So they're all methyls, so we don't have to really arrange them in any like alphabetical order. So, but we are going to minimize the mentioning of the word methyl, right? So, and how do we do that? By using the Greek prefix, right? Which is going to be tri, right? So you have like di for 2. So if you have 3 identical substituents, you can use the prefix tri. So you have trimethyl as part of the name of this compound, right? So you can think about the building blocks of the name in your mind, right? So like there is no particular order in which you need to think about it, but you need to write them in a particular order, right? So if we have 7 carbons in the alkyl chain, right? So what does it mean? So it's going to be heptane, right? So we'll have heptane as part of the name. That's going to be another building block of the name for this alkane. So heptane, trimethyl will be another part. And then finally, we need to indicate the kind of like houses, right? So 140 Flag Road, right? So here, like the numbers of the carbons will go first, right? So we'll need to entail 2, then 4, and 5, right? So these are our carbons. So 2, 4, 5. So all of them will contain the methyls, right? So we don't have to say 2-methyl, 4-methyl, 5-methyl, right? That's going to be too much mentioning of the methyl. We're going to condense the like name, right? Because it's already very long. So let's take a look at how we're going to write out the name. So we're going to erase our part A, and we are going to minimize the mentioning of the word methyl. So let's take a look. So 2, 4, and so 2, 4, 5, right? That's where the methyls are located. So maybe let's try to like do something like incorrect here, right? So on one hand, it's tempting to do something like that. So 2-methyl, right? So there is on the second carbon, there is methyl, right? So you need to think about this, like on the second carbon, there is methyl, not like methyl on carbon 2, right? So you need to kind of like switch words here, but the meaning will be the same. And this switching of the words, that's what the convention requires, right? Maybe 2-methyl. Then again, we'll have 4-methyl, right? So I'm writing this in the red font. You need to be on the alert. So because it's incorrect a little bit. So, and then 5-methyl. 5-methyl heptane, right? So that's not quite what we're looking for in the name, right? So the methyl word was mentioned too much, right? So we're going to modify that, and then we're just going to combine those 3 methyls into the trimethyl, and then we'll show where those 3 methyls are located with the numbers that will show up before the part trimethyl. Okay, so let's erase that. We'll keep it kind of like in mind. Okay, so now we're going to switch the font. And where's this coloration eraser? Oh, here we go. Okay, so the numbers where methyls are located, right? So you can all combine those methyls into trimethyl because all the methyls are identical to one another, right? So then we need to show where those 3 methyls are spread, right? So if we show the numbers such as 2, 4, 5, right? So then it will give the hint to the reader that carbon 2, carbon 4, and carbon 5 all contain some substituent, right? So then what are those substituents? So total will have 3 methyls, so we'll say it as trimethyl, trimethyl. So as you read it, right, what's going to happen is that you will know. So 2, 4, 5, 3 carbons, right? So we'll have substituents. And then, so this trimethyl part will say that you will have total of 3 methyls on those 3 carbons, right? So this will be quite unambiguous because you cannot quite put them into like any other way. If you somehow decide randomly to attach you can say, okay, why should not I attach, for example, 2 methyls to carbon 2 and only 1 methyl to carbon 5, right? So this will not make sense because number 4 will be excluded, right? So, but that's going to be the only way to kind of like distribute those 3 methyls. You must have 3 methyls spread, right, amongst carbons, 3 carbons, 2, 4, and 5, right? So then it means that each of those carbons will have to contain 1 methyl, 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 and methyl, right? Which is what you have in the actual structure. So yeah, this is kind of going to be kind of like new to some extent, but at the same time, this also like doesn't have any ambiguity in the naming, right? So we'll take a look at like more examples of that kind just in this session. So trimethyl, what's the longest chain? It is heptane, right? So 7 carbons, trimethyl, 2,4,5, trimethyl heptane. So no any other like options are possible here. So yeah, that's like pretty much as far as the like potential combinations go, but you cannot like make anything else out of it, right? So even if that seems kind of like piled up, so yeah, there is no ambiguity anyway. You can like try to like make it different, but it will kind of like not happen, right? So if you want to have like maybe 3 methyls on carbon number 4, you will not be able to do that either, right? So if you put 4 methyls here, right, so then you will just make like a pentavalent carbon or something like that, right? So that's not possible. So then the only way to go about that is just to have methyl, methyl, methyl on each of those carbons, on carbon 2, carbon 4, and carbon 5. Okay, so anyway, could be a little bit more time this time around, so but yeah, everything will be recorded, so you're welcome to like leave anytime you want. So if you need to like run somewhere, break your fast or eat or something, so that's all good to go. So now let's take a look at more examples. So there was something exciting that you saw in practice exercises, and this looked like that. Okay, so one more structure. So let's move on to the third structure. So I think we'll have time for that. So pretty much we're trying to identify the longest chain, substituents, number the chain correctly, and combine those substituents to the extent we can. Right, so here we go. So what do we have? Okay, so I'm going to draw something like that. So we have CH3. So then we have CH2. It's potentially going to be more complicated than on the exam, but yeah, that's how it is supposed to be. So then we have the so-called quaternary carbon. Quaternary carbon because it has like 4 substituents different other than H attached to that. So C, CH2, CH3. So then we'll have another ethyl, CH2, CH3. So there's going to be quite a bit of writing going on. So, but it's okay. And then we'll have CH. And then you have like a variety of building blocks, right? A variety of building blocks that you can encounter like as alkyl groups names. So this is also nice. Okay, so I think that this is the one. So let's take a look at what is going to be the longest chain here potentially. So there are many like ways to like look at the longest chain, right? But we need to just count the carbons, right? Like from like various directions. So we have 1, 2, 3, 4, 5, 6, 7, 8, right? So that is like a candidate potentially. So, but let's see if we can find something longer, right? 1, 2, 3, 4, 5, 6, 7, 8. So 8 again. That seems to be shorter. So let's take a look at another approach. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So again, so like 9 carbon seems to be the longest chain, right? So this methyl and that methyl are identical. So if we like end up choosing like this one, right, or that one, doesn't matter, right? So they are going to be identical. So now let's try to number those carbons, right? So what's happening here? So we can start from this end, right? From kind of the left side, we're going to move on. The branching starts potentially 1, 2, 3 on the 3rd carbon, right? So if we start moving from here, from the right side towards the left, let's say this is 1, right? These are identical methyls, right? 1, 2, right? On the 2nd carbon, the branching will start. So let's like start it from the right. So it looks like this direction wins. The branching starts on the 2nd carbon, so this will give the like rise to the fact that we will minimize the numbers, right? So that will be present. So in our situation. So let's see what we have. So and then yeah, we'll actually check, right? So if that's going to be the case. So let's take a look. So let's say maybe we have here 1, right? 2, 3, 4, 5, 6, 7, 8, and 9, right? So this is going to be our longest chain. So 9 carbons, 1, 2, 3, 4, 5, 6, 7, 8. Yeah, so this is not the longest one. So longest chain, so that's going to be like one way to think about it, right? So now what is next? So next we're going to take a look at another situation to kind of like, what's it, to number the chain. So let's maybe switch the colors here, right? So, and yeah, we can also circle the substituent. So there is no, again, particular order in which we can do that. So it's going to be 1 substituent. So then we'll have more substituents here. So then we'll have a methyl. And we will also have an ethyl group right here. So if you think about it, that's not the part of the longest chain. So yeah, these are our substituents, right? Total of 1, 2, 3, 4, 5. 5 substituents, quite a bit. So very branched hydrocarbon right here. So we have 2, looks like then 4, right? If we count 6 and 7, right? So okay, so that's going to be our longest chain. So we found all the substituents. We numbered the chain closest to where the branching starts, right? So 2, 4, 6, 7, right? So in terms of substituents, we have methyl, methyl, ethyl, ethyl, and ethyl. So these are our potential groups right here. So then let's take a look at the names, right? So also the longest chain will contain 9 carbons, right? So in our nomenclature rules, so if the alkane chain contains 9 carbons, this will be known as a nonane, right? So nonane will be the name. So, or will be part of the name of this huge hydrocarbon. Okay, so now let's take a look at the substituents. So we can show what's that. So there is no particular order in which we need to put them, right? But let's take a look at the alphabetical order, right? So we have methyls now and ethyl groups. So methyls will be later in the alphabet, so we'll start putting ethyls first, right? So then what's going to happen is that we have 3 ethyls, right? So if we have 3 ethyl groups, we'll use before them in the name the Greek prefix tri, so triethyl, right? So let's just put it here somewhere, right? So triethyl will show up before dimethyl, right? So tri and di don't count as the alphabet things, so it's going to be only the names of the substituents themselves, such as ethyl and methyl. Ethyl comes before methyl, right? So we'll have triethyl. So also, we'll need to show where those 3 ethyls are located. So if we count the numbers, right, it looks like ethyl is located on carbon number 4, right, and carbon number 6, right? So we can theoretically say 4-ethyl, then 6,6-diethyl, right? So, but what's going to happen is that we can condense that, right? So how do we do that? So we'll just put the numbers together where all the ethyls are located, right? It's going to be 4, 6, 6, right? 4, 6, 6 triethyl. So that's going to be our situation that we're going to have, right? So basically it means that there are ethyls on carbons 4, 6, and 6, right? So total you have 3 ethyls, right? So what's going to happen? So if you have this kind of a repetition of the numbers 6 and 6, it means that this carbon number 6 will have 2 ethyls, right, on it. So consequently, the only option to kind of place the leftover ethyl will be carbon number 4. So 4, 6, 6 triethyl. If you try to hypothetically put 2, let's say, ethyls on carbon number 4, right? So in this case, you're not going to be able to do that. So because how are you going to share kind of the remaining 1 ethyl for carbon number 6, right? So if you, let's say, have 4 ethyls on carbon number 4, then your name would sound like 4,4,6 triethyl, right? So yeah, this is going to be our situation that we are going to deal with, right? So 4,6,6 triethyl. So once again, to reiterate, you'll have 1 ethyl on carbon number 4. You will have 2 ethyls on carbon number 6. Hence the piece 6, 6. Okay, so 4,6,6 triethyl. So no any other combinations are possible. So we'll just go with that. So anyway, and then we're not going to say 4-ethyl, 6-ethyl, 6-ethyl. That's going to be too repetitive and against the rules. So 4,6,6 triethyl. So then what about the methyls, right? So similar situation will happen. So total we have 2 methyls. Consequently, we can combine them under the umbrella of dimethyl. So now, where are they located? On what carbons, right? Carbon names, carbon numbers will go first. So these are carbons 2 and 7. So then we'll continue the name 2, 7, right? So 2, 7 dimethyl. So dimethyl part will mean that we'll have 2 methyls total, right? 2 and 7, that's where those 2 methyls are distributed, right? So again, if you try to somehow just think about some potential combinations, right? Because why not? So you cannot put 2 methyls on carbon number 2, right? because carbon number 7 will have no methyls, right? Which will kind of not make sense, will not be in agreement with our like actual structure, right? That we're trying to name. So consequently, you cannot also put 2 methyls all of a sudden on carbon number 7, right? Because carbon number 2 will have no methyls in this situation, because total will have 2 methyls only to distribute between carbons 2 and 7, right? 2,7-dimethyl. 2,7-dimethyl. Finally, so the last part will be our what? The last part will be the main chain, right? So main chain name, so that's going to be having like 9 carbons, so nonane. So nonane, so I think that's the one, right? So decane, it's when you have 2 carbons, no, 10 carbons. So nonane, it's 9. So it starts with the same letter, nonane. So nonane, that's it. So, and you have it here, right? 4,6,6 triethyl. So 3 ethyls are amongst carbons 4, 6, and 6. 1 on ethyl, 2 on 6, right? So that's kind of like making sense. No any other options you can like have here. So 2,7-dimethyl. So total 2 methyls distributed between carbons 2 and 7. So 1 on 2, 1 on 7. So nothing else is possible, even if theoretically we can like reconnect the parts, right? And then carbon number 7 all of a sudden can have 2 methyls, but the structure doesn't have, right, 2 methyls right here. So then was at nonane. So we have the longest chain here containing 9 carbons, nonane. So again, so this one is a little bit more complicated, right? So we'll have something kind of, again, more straightforward on the exam, just in the interest of time. But here we, again, think about where to place, right? The substituents, various like alkyl substituents in this situation. So we think about their names, right? How they're alphabetically located, E, M, right? We think about the Greek prefixes, tri for 3, di for 2, right? So then I think that's it. So that's what we're mostly going to use at this point in our careers, right? And then you have the numbers, right? 4, 6, 6. So these are the numbers of carbons where those substituents are distributed, right? So finally, so you have nonane here, so which is going to be the name of your longest chain. So 9 carbons, nonane. So ane, that's going to be the ending, right, for the like alkanes in general. All right, so then what else? So there is a little bit of the emergency going on. Sorry about that. Okay, but I think I don't have to immediately go there. All right, so now now we'll go to the next topic. Okay, finally. So this will be a little bit less time consuming, and this will be now about the solubility, right? So the solubility thing is a kind of very popular topic, I would say, and this spreads from, let's say, like this chemistry to like other chemistries as well. So let's take a look at that. So it's going to be our like fourth potentially or whatever. Concept. So we're going to look at the functionalized alkanes, so to say, right? So let's take a look at something like this with an OH group, right? So then it's going to be like another alkane without any alcoholic groups. It will look like that, right? So then we'll have another one with the 2 alcoholic groups, and it will look like this. So let's say OH and OH, right? So let's take a look at what happened here. Maybe we'll modify that a little bit. So this carbon, so speaking of your skeleton structures, contains 6 carbons, right? Or this alkane rather contains 6 carbons. So let's make them all contain 6 carbons. So it's going to be like this: 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, great, right? So and then we'll add another functional group right here. So still 6 carbons, 1, 2, 3, 4, 5, 6. O and O, right? So here we don't have any carbons, so we have the oxygen, right? It's explicitly shown. So consequently, on this terminus, you don't have carbon, you have the oxygen, right? And then you have 1, 2, 3, 4, 5, 6, 6 carbons. So both of them, so all of them can be like thrown into water somehow, right? So let's try to rank them in terms of solubility and goodness, right? So um, 1 being very good, 2 in the middle, 3 very poorly soluble, right? So in this situation, we're going to start with just a like pure alkane. So for instance, here this alkene contains 6 carbons, right? It has no OH stuff attached to that. So potentially it's going to be like not very like water. Remember, so in this case, we're going to like also use this rule, like dissolves like. And here this alkane is like not like water at all. So then let's see. So it only contains carbons and hydrogens. So potentially, if we just look at those structures, so they will be like more soluble in the water than this alkene in the middle. So let's assign this guy the solubility rank number 3, the poorest soluble out of those options, right? So 3 poorest, 1 best. So now if we compare alkanes top and bottom, right? So they both have the like alkyl chain with 6 carbons, right? So that's really kind of like not so good for the solubility, and we cannot really like compare them, right? So saying, okay, well, one has more carbons, one has less carbons, right? So the more carbons there are, so the less the solubility will be generally, right? So that kind of like doesn't like really help. So now let's take a look at the OH groups. OH groups provide the similarity to water, right? You can remember this rule, like dissolves like. So here's your water structure right there, right? So now this like compound on the top contains only 1 OH group, right? Compound on the bottom, if you think about it, contains 2 OH groups. So who is more like water? Who has more water character, right? So looks like the compound on the bottom has more water character. So the compound on the top has some water character, but a little bit less, right? So it will contain only like 1 OH group. So potentially, so this compound on the top will be better soluble in water than compound like in the middle. So let's assign it the solubility class number 2. Finally, so the compound on the bottom will have the solubility class number 1 because it has like more water character, just 2 OH groups, right? If you think about it, and then it will be more soluble in water than any of those compounds, right? So then you can think about the bonding, right? So formation of the bonds. Let's say you think about the molecule on the top versus water, right? So what kind of bonds are they going to make, right? So just think about the scaffolding of the principle. So here you're going to form the hydrogen bonds. So this is the bond, right? So delta minus on the oxygen, delta plus on the H. Then you surround it with another water molecule, right? And then you can have it here, right? So you have just like at least like 1 hydrogen bond potentially between O and H, right? Delta minus, delta plus will interact with one another. So one hydrogen bond can be formed between this compound, right, on the top and the water molecule, right? So typically we try to just confine ourselves to 1 hydrogen bond between the hydrogen bonding groups, right? So then if we take a look at here, right, so we have 2 hydrogen bonding groups, so potentially they can bond with 2 molecules, right, of water. So let's make it happen. So here we go, right? So maybe it's going to be looking something like that, not here, but like OH will have delta plus, O minus will have delta minus, right? So then we can like put the water molecule here, and we can also put the water molecule here. So as you can see, so already from this drawing, it's kind of like visible that we can potentially surround this molecule on the bottom with a lot more molecules of water per molecule of the organic compound, right? So then this kind of like molecule by itself, right? So we'll have more potential interactions via hydrogen bonding with the water molecule, right? So if you can do that, so if you can kind of like increase the amount of interaction between a particular solid and the solvent, then you will have better solubility, right? So because remember, so the better the the solid can interact with the solvent, the better it will be soluble in this particular solvent. So more interactions means kind of like higher strength of interactions and better solubility as a result. If you think about the other direction, right? If you have like an alkane, right? So that cannot bind with hydrogen bond and with water at all, then you will likely conclude that, okay, well, there is going to be like very poor solubility, maybe like not solubility at all. And then you will have two layers, layer of water and layer of alkane when you try to mix them, right? So those compounds, speaking of terms, will be immiscible, right? So then this compound on the bottom, right, that has two alcoholic groups will potentially be miscible, right, according to our kind of like explanations and arguments. Then compound on the top will only have one OH group, and then will potentially form one like hydrogen bond with the molecule of itself and the water, right? So this one, so one molecule of the organic compound can bind with two molecules of water, right? So more strength of the interaction, more interaction in general, higher amount of interaction, more strength like between the solid and the solvent, better solubility, right? So yeah, just something to think about when you like try to kind of answer some like ranking questions, for example. So yeah, anyway, so that's our solubility situation here. You can also think about like delta minus, delta plus charges. How are they produced? So that should kind of like bring you back to the polar bonds, right? So as you can see, anyway, so we can go like infinitely almost to those kind of like things, right? So, and then at the same time, it's going to be like a good thing for you to think about, okay, well, what should I review, right? So if I want to like explain something, so I can potentially go in depth, and then, yeah, you will kind of like potentially and like find some concepts which are unfamiliar to you. Then this is something that you can review, right? For example, if you don't recall how those delta plus, delta minus charges are formed, right? So then, well, it's going to be something for you to review. So the polarity of the bond. Why is the bond polar? Because, for example, two atoms can have different electronegativities, right? So to some extent, that makes the bond polar, and so on. If they're like two atoms, such as CH, have like very close electronegativity values, so what does it mean for the polarity of the bond, right? So there are many questions that can be like asked. Anyway, so now finally our like last topic that we want to encounter is going to be the burning, right? So, or some like reactions, right, of organic compounds, such as oxidation of alkanes, right? We're trying to make the interaction happen between the alkane and the oxygen, right? So here, let's take a look at two examples, actually, right? So we can have the complete or incomplete burning of the alkane. So the same alkane will be chosen, such as pentane, let's say part A. So that's our P5, potentially problem 5. Part A, so C5H12, right, is going to burn, right? It's going to interact with oxygen. And then as we know, right, we have two options, right? So complete burning or incomplete burning, right? Complete burning will lead to CO2 and H2O formation, right? So as a matter of fact, for all the alkanes, this will be true. So if you burn like any alkane, you will have CO2 and H2O. The only difference will be, yeah, this formula, right, of the respective alkane and stoichiometric coefficients that we are going to use, right? So here we're going to balance it by inspection using the whole numbers, right? So 5 carbons, 1 carbon. So let's make it 5, right? So how do we do that? By means of stoichiometric coefficients, right? So 5 carbons. So we cannot make it like C5O2. That's going to be like an incorrect formula, but we can put the 5 in front of CO2, right? So that way we will have 5 carbons, but at the same time, we'll also have 5 by 2, 10 oxygens, right? So then we have 12 H's here and only 2 H's. Then we're going to kind of like bump up the number of hydrogens, right? So to match it with the like larger number of hydrogens. So 12 H's, 2 H's. Let's put 6 here, okay? So now you have 5 carbons, 5 carbons. You have 12 H's and 12 H's. So now you have a lot of oxygens on the right, as we can see. 5 multiplied by 2, 10. 10 plus 6, 16. So 16 O's on the right, 2 O's on the left. So let's put 8 here. as a stoichiometric coefficients, we'll have now 16 oxygens on the left. Very good. So now let's think about another option. So option B. So this is complete combustion, right? Means you're going to form CO2, right? It's going to be kind of like a complete. You can think about this that way, right? So all the kind of like carbon valences were complete with the maximum number of oxygen atoms that could be attached to the carbon, right? So now incomplete means you are going to produce in all those cases CO2, I mean not CO2 but CO, right? So I'll try to specify it in the questions, but typically, or in a lot of cases, when you have the incomplete combustion, it will be hinted, right? So you're going to make CO and then water will still be made, right? So that's going to be the case. So CO, you see here, we have 2 oxygens, but in this case, we have only 1 oxygen. So we are kind of incomplete, right? Because carbon only possesses 1 oxygen in its structure. So CO plus H2O. Water still will be formed, just regular water molecule, nothing else, right? And that's it. So C5H12 plus O2, that's the only difference. We have now CO, right, instead of CO2. Not a lot of oxygen, only 1 out of 2 possible that can be attached to carbon when you form oxides of the carbon, right? So let's take a look at what happened here, right? So in this situation, we have 5, 1. Let's make it 5, okay? So 5 carbons now. So in terms of oxygens, we have how many? So, or hydrogens, right? So we have 2 hydrogens here, so 12 hydrogens on the left. So what do we need to do? So we need to bump up the number of hydrogens. So 12 to, let's make it 6 waters, right? That will give us, in turn, 12 hydrogens. 12H, 12H. So finally, carbons, I mean oxygens, 5 plus 6, 11, right? So here we have technically 5.5, but we typically don't use the fractional numbers, right? So consequently, we're going to multiply everything by 2, right? And then we'll get rid of 5.5. So let's do that. So you can take, or you can show this like arrow at the end of the equation and then multiply by 2. It means that you're going to multiply the entire equation by 2, right? So, and then you're going to have 2C5H12. 5.5 multiplied by 2 becomes 11 O2, right? This is oxygen. So then 5 multiplied by 2 becomes 10 CO. And 6 by 2, 12. So 12 H2O. So then, yeah, here you go. You burnt it. These are the minimal possible coefficients still, which are whole numbers, right, by our agreement. So, and that's it. So if you recount everything, so we'll have 10C, 10C, 22O, 22O, 12 by 1 plus 10. So 22. And finally, we have 24 H's. 24 H's. So this equation is balanced, right? So the number of each atoms of each element is the same on the left and right side. So we balance with stoichiometric coefficients, which we can put in front of the chemicals, right? So don't try to balance it with what's it called, subscripts, right? So don't do that, because if you try to make it maybe, let's say C5O2, right? So that's not going to be possible. That's unreal. So you don't have such a compound of C5O2, right? But you can have, for example, like 5 molecules of CO2. That's fine. You can have like 3 molecules of CO2 and so on. That's what the stoichiometric coefficient will do, as much as it's tempting to put the 5 as the underscore, right, or subscript. So yeah, that's your complete, right, CO2. Incomplete chiefly produces CO. Sometimes the incomplete combustion can also produce carbon, right? So, but we'll not be looking at that case. I think it's enough to have those 2 options. And if anything, I'll try to like specify what you're going to make in terms of the incomplete combustion. Complete combustion leads only to CO2 and H2O in all of those cases, right? So yeah, and I think that this is it for now. So we had a little bit of the extension of the time here, but it's okay. That happens. And now we're going to stop recording and have a good Friday. Bye, everyone.